All right, how is everybody today? So who has not been to one of these unstructured data meetups before? Raise your hand. Wow, lots of new people. Thank you so much for coming. My name is Chris Churilo, and I work at a company with a really funny name called Zilliz, Z-I-L-L-I-Z. And we are the open source maintainers of another project called Milvus. Milvus is an open source vector database. We donated the project to the Linux Foundation a few years back. And when you do that, you don't get to use the name anymore. So that's when our engineers came up with this really goofy name, Zilliz. So it's a palindrome. They're really proud of themselves. I always like to tease them and say, why Z? Why not A? But here we are. So thank you so much for coming to our Unstructured Data meetup. And at the end of the meetup, I will give you guys an opportunity to share any job openings if you have it. So just raise your hand and I'll hand the mic over to you. And really, if you've been to one of these meetups, you've heard me do this talk. I'm actually going to do a little bit quicker version of this talk. And just explain why we call this meetup Unstructured Data. So we could just call this the Milvus meetup, but really that would get really boring really quickly. Probably after a couple of meetups, everyone become Milvus experts and then we're just done. But when you think about what's actually happening in the GenAI space, there's actually three big pillars that we think that there are some opportunities for developers like all of y'all. So of course, when we think of GenAI, there's all the models. And I've talked with some of you today. There's a lot of models, a lot of activities happening. And these names are, what you typically see. And of course, there's the hardware side, right? Computation. But really the third leg or the third pillar of GenAI is all about data. And of course, as a vector database, we like to, make sure that everyone understands this is where you put your vector embeddings. However, there's actually a lot more in this data space that we want to encourage developers to build on. So there are still a number of tools that are needed for data encryption, for building out pipelines, for security, for governance, observability. I was actually just talking to this gentleman, Dilip here, about observability, because that's something that his organization does. And at the last Palo Alto meetup, we actually had 2 talks that focused on security and governance. And it's tricky. It's really, really tricky. How do you ensure that data that's going into your RAG solution is only for your eyes? It's not as easy as it sounds. So we want to make sure that we host these meetups so we can bring a lot of developers that are working on some of these tools together so we can network and we can build the next great set of tools for unstructured data. So if you are working on a project and you'd like to present at one of our meetups, just let me know, or any of the other Milvus people here, Milvus or Zilliz people, and we're happy to have you. So we host these meetups here in San Francisco, as well as in Palo Alto, New York City, Berlin, Seattle. We just did one in Brazil, and then a couple in China as well. So it's developing into something that's really exciting, and it's a lot of fun. And it's also about community building, right? The more we all get to know each other, the more we're going to share, the more powerful these applications and tools are going to be that we're building. So it's pretty important for us to make sure that we can build out this community. And of course, right now, RAG is still the hot topic. And last year, we were all kind of getting to know text-based RAG. This year, everyone's talking about multimodal. In fact, all 3 talks are going to have some kind of multimodal RAG talk, because it's exciting, because there's a lot of really cool things that are happening. But this is just the beginning. Next year, is it going to be connected with recommender systems? Is it going to be, something entirely different? So I think what I want to leave you guys with is I hope that these talks inspire you to build something cool. And then you come to these meetups and share with everybody, because we have a long ways to go. So one last thing before we get started with our first speaker. Of course, if you can give us a star, if you can like us, we work really hard on the open source project. You can take this barcode, this QR code, and it'll take you to the repo. And then Sachi, who's got the camera running around here, what she's going to do is she is going to do a little raffle and give out some swag. Okay, so let's get started with our first speaker. Robertson, you want to head up here? All right, Robertson is a solution architect, at Marqo. And he's held solution architect positions at AWS, Stripe, and a number of other places. And so we made a little bit of a change to the agenda, but he was kind enough to go first. And with this, let's just have him get into the talk. It'll switch. Let's try it again.
In a second.
Or you can sing. Are we doing something wrong?
It may have gotten disconnected from the adapter there. Try the cable at the adapter. No, just in your laptop.
Ah,
yep.
There we go. All right, thank you.
Yeah, so just a little bit about me. I'm Rob. I work with a company called Marqo, and we work with embeddings from end to end. So we start at the training layer and we go all the way through retrieval, returning documents at the end of the day. And Python quit unexpectedly. That's fine. Cool. And a little bit about Marqo. We were founded in 2022. We have headquarters in San Francisco, but we also have engineering in Melbourne and London. And we've raised about $28 million. And we have developers, over 1,000 developers using our open source or cloud solutions. And we publish a lot of stuff open source. So most of the stuff that I talk about today is available open source. The data sets that we talk about training with, you can find in our repo. And yeah, if you want to get started with Marqo, it's there as well. And we break this down into 3 different problems. So there's retrieval. Everyone, I think at this point, knows about approximate nearest neighbor search. You put embeddings in, do ANN, get things back. And it kind of gets a bad rap sometimes. People think it's a little bit slow. And what we found is that it's often not the ANN that's slow. It's the combination of having some sort of orchestrator that winds up talking to inference, that winds up talking to first stage re-ranking, that winds up talking to metadata retrieval. And this latency plus serialization and deserialization winds up making things kind of slow. So we wind up doing embedding as well. But most of the talk today is going to be about model training. If you put garbage in, you get garbage out. And a lot of our work has been on creating multimodal embeddings that have some notion of rank and take into account user interaction data. And we're going to break down how. If you want to read more about how after the talk, there is also an archive paper. You can take a look yourself. But yeah, we handle training. And the reason that we handle training is we found that there are a few problems with the way that these multimodal models in particular are trained. Most notably, we kind of split into 4 categories. The first is that there's a poor intramodality understanding. So if you take a look at the way that clip models are trained, which we'll do in a minute, there's not great text-text understanding. And most of the text-text understanding that is there is actually incidental. And then if you go on to looking at multiple fields, it doesn't often take into account images and text combined. And as you start to get more and more fields like you would in an e-commerce system, you might have title, you might have a description, you might have reviews, you might have an image. Having some way to combine these into a single vector representation becomes important for retrieval. And the reason that this doesn't happen in the existing models is there's this binary relationship that's present in clip training. We take a text pair, we take an image, and all of those pairs that we have are put into a contrastive learning training regime. And we learn really well what text is related to what image, and we'll see how that happens in a second, but we don't really learn what queries are related to which texts and what queries are related to which images. And this is why, if you take a look at this architecture. We have a very standard two-tower model. We have a text encoder, we have an image encoder, and along that diagonal, we want to make sure that the distance is minimized because that diagonal represents text and images that we know are related. And it distances all the others. But what you get at the end of training is, if you look at the graph, you have that dog, and you have the text that represents the dog, Pepper the Aussie pup, and it's relatively co-located. But there are a few problems here. So if you search for SLR camera and want to do retrieval with a clip model, it'll do a great job at finding things that were labeled SLR camera. And like similarly, if you have like a stock image site, this is like a great use case where your stock images might be captioned the same way that models, or the same way that items in the training set were captioned, and the retrieval works pretty well. But what's missing is there's a ton of unstructured data that people have that goes kind of unused, that could be used. So in this case, we have 1,347 clicks when someone searched for SLR camera, and we might have multiple images. We might have a description. We might have product details. And what people typically do today is just vectorize an image, take in a piece of text, and all of that data that could be used kind of goes missing. And yeah, this is because of the binary relationship training, and there's no way for the clip model to really disambiguate between different cameras in the data set. So if I'm Best Buy or if I'm a high-end camera retailer, the objects that I want to return are probably very different. Like if someone searches for camera on Best Buy, they might be looking for something much cheaper than if someone goes into a store searching for $5,000 cameras. But this notion of rank is just completely missing. And if that notion of rank is missing, you can't just expect for a re-ranker to handle the problem. You have to actually get the candidates to the re-ranker for everything to work. And while we're going to focus on multimodal, the same problem also exists in text. A lot of embedding models do a really good job at this one-to-one relationship. And if you have a question that has a discrete answer, then this works pretty well. Like if I want to ask what the atomic weight of gold is, there is a correct answer. And if I'm doing some sort of RAG app and I pass it on to the model, it'll do a pretty good job of answering whatever question that I had related to the atomic weight of gold. But a lot of queries are actually one-to-many. So if I search for Olympic medals 2024, there are a couple of different information needs that could be related to this query. If I'm on an archery website, I might want to know about individual medalists who are competing in archery. But if I'm on Google, I might just want to understand which countries or how the countries are doing individually. And because we don't have any notion of interaction or what's actually relevant to people in a given domain, the model doesn't have any way to actually figure out which of these documents is most relevant. And this problem only expands as you have larger and larger corpuses. So now that you kind of see the problem, I'll break down a little bit of the story that led us here. We were working with an e-commerce customer who had tried to use off-the-shelf clip models. They had gone with an Elasticsearch solution, and what they saw was a double-digit drop in relevance, and that, or double-digit drop in add to cart. And that's because with RAG, we're working over a lot of problems that don't have really tuned retrievers. But if you're in e-commerce, how well your search does, how well your recommendations do, directly affects your bottom line. And it's been tracked for decades. So a lot of these incumbent retrievers, even if they're lexical, have been tuned over like 20, 30 years. They have really built out synonym lists. They have really built out re-rankers. They really understand which documents should be presented. They understand which of the metadata should be searched over and which of it actually degrades relevance. And we wanted to get them to use their unstructured data. And what we came up with is a way of training the model that's still a two-tower model, but actually takes into account a number of different pieces of information. So we have this text encoder, but instead of just having a caption on the left-hand side and an image on the right-hand side, we actually bring in fusing these different pieces of metadata into the training process. So here we have a cat, we have a title that represents the image, we have a query that's returned the image, and we also have a score to weight function that kind of encodes this user interaction that we were talking about before. And by combining all of these pieces, we start to get a more full picture of what data we're actually querying over. Because we're fusing the embeddings here, we can actually incorporate an arbitrary amount of metadata into this right-hand side. And the left-hand side, again, here it's a query. It doesn't have to be a query. You can put what you want there. But what happens training this way is we get this intramodality understanding where we now start to move the embedding space so that the query, the title, and the image that it represents are all relatively co-located. And as we start to expand this and expand the actual size of data that we're training with, we can start to get a better representation of what fusing these embeddings should actually look like. And this winds up being important in practice because this is what people do. If you look at any e-commerce solution that's using vector search today, what they're doing is they're taking in a name, they're taking in maybe a description, maybe they're taking in a category, definitely taking in an image, and they're combining these vectors together. But what's missing is during the training process, the model doesn't ever actually learn this representation. And so by doing it this way, we start to get a better understanding of how we fuse them. But on the right-hand side, what we have is very similar to a collaborative filter. So if you're familiar with recommender systems, the idea is we want to take user interaction data and products, and we want to start to factorize these different components so that we can learn based on the products that we have today, which users are they relevant for. Here we kind of generalize that to embeddings. So based on a query and embedding pair, how relevant is that embedding? And you can kind of think of it as understanding the angles of the embeddings relative to a given query. And what happens here is this gets us a notion of rank. So the different angles wind up being the way that we can actually infer this rank in the embedding space. That was a lot of words, so let's use an actual example. Here we have someone, let's say they're searching on Canva. I don't know why I'm pointing at my laptop. Let's say they're searching on Canva, they're looking for quote bubble, and they want to put something into a slide. We have 4 results here in this carousel, but all of them look like quote bubbles, but only 2 of them are things that people actually wind up using. So even though like graphically they look relevant, let's say that these 2 items aren't actually things that people click on. We can infer from like a number of user selections what is actually relevant for a given query, and we can start to aggregate scores per query. And before we go on to training, we can split this aggregation into two different sets. So we can have novel queries if we do a split post-aggregation, and we can use those to evaluate the model at training time. What we're aggregating with is the scores. So here, a score could be 5 clicks, it could be 3 clicks. The training regime that we have doesn't really care what the score is, it just cares that there is one. And we can use this score to actually infer how strong the relationship is between a given query and the items that it returns. And so we can go through the training process. We can use individual queries to understand where that triplet should be. And then we can use the scores to infer the results. We have those 2 matrices that we showed a second ago. And then we can do inference, evaluate the model, see how things are going, and then evaluate across 4 different domains of in-domain, novel corpus, novel query, and zero shot. And after we do this, we start to have that ability to fuse data both at storage time and query time. So we get this description, we have a title, we have multiple images that might represent a product, and we can use an arbitrary number of these. And then we can use any number of images and text to actually represent the query. And the reason that's important is, Chris actually alluded to it at the beginning, these are becoming more and more like personalized real-time recommenders. And as you start to understand what someone's interacting with in your website, you can actually start to capture those IDs, use the actual embeddings to pull the centroid of the user to a different point in the embedding space. What we've seen results-wise is a really dramatic increase in NDCG. That's not super surprising because NDCG captures like a metric around rank, and we're incorporating rank into the model. In domain, we do really well. We have, a 6x increase over pre-trained models. But it does generalize to out-of-domain things as well. So in the novel query side, we still have almost 3x better performance. Novel corpus, same thing. And even for zero shot, we still retain the NDCG improvements. And yeah, it winds up working pretty well, and we see really similar results in practice. The other thing about training this way is it lets you capture a broader range of tasks with your embedding retrieval. I'm not going to talk through every one of them, but let's pick some relevant ones. Recommendations. Because we start to have this better intramodality relationship, and because we know what things are related, we can start to build real-time recommenders. So I can understand that this lens is related to this camera, and when someone searches for SLR camera, I can actually show this to increase result diversity. We can also do things like conditional search. I think this one is really underexplored, but if you've used like any of the E5 models, you're probably familiar with this sort of syntax where you can just give a prefix, and at training time, you can actually learn different subdomains as part of training. So one way this could be relevant is in a given marketplace. Like let's say we have a marketplace that operates out of Miami and a marketplace that operates out of London. When I search for winter jacket, I mean two very different things. And the model can actually learn that during training. This can also be used for things like specifying that something is for a query or specifying seasonality. Like all of that can kind of be encoded into the prefix. And yeah, classification is also a pretty good example. It comes up more than you would expect, where a lot of businesses have really rigid taxonomies. So if you're like Amazon.com, you probably have some A/B testing about how well your taxonomy actually does. But the ability to go through your product catalog and do real-time retaxonomization is really powerful. And if you train models for classification, you can start to capture some of that ability to test new classification taxonomies on the fly. Here's an example of real-time personalization. So you can see that the queries are actually the same. So when I search for backpack here, I have 4 items in my context. They're kind of neutral, very minimalist, like one zipper. And we get back a set of very similar items on the left-hand side. On the right-hand side, we have 4 outdoor backpacks. And by adding a small weight, like this isn't like saying it's 50-50 split here. It's just pulling the embedding space just slightly towards things that someone's interacted with. We get back a very different set of results. I think this is alluding to the last talk, so I won't go too deep here. But another thing you can also do as part of the training process is actually do training around binarization and dimensionality reduction. Much like embedding models aren't trained to fuse different embeddings together, they're also not trained for binarization or reducing dimensionality. And what we've seen is that incorporating the transformations that you want to do on the embeddings during training time improves performance really dramatically. And by really dramatically, I mean really dramatically. So these are both GCL trained models. So they're using the same training process we've been talking about before. But on the right-hand side, we have on the top a Matryoshka representation. So here we've reduced dimensionality by half on the furthest left set of bars. And you can see that there's a slight increase in performance, not statistically significant if I remember correctly, but like very, very comparable performance at this 50% reduction in dimensionality. And as you go through and keep doing this dimensionality reduction, you can see that we retain performance really well. Oh, sorry, I'm misremembering this graph. The GCL on the left-hand side is Matryoshka reduced without training awareness. So you can see by 128, so as we've reduced the dimensionality by 8x, the original model without Matryoshka-aware training has reduced in performance by 50%, whereas the original model retains almost all of its performance. Binarization has a very similar pattern where you can retain a lot of the performance of the model just by teaching it that you're going to be doing some sort of transformation post at inference time. And if you take a look, whether or not this is valuable is really dependent on domain. If you're an e-commerce customer, these slight reductions in performance probably have like a very significant monetary impact. Whereas if you have a really large corpus and you need to store it without paying, $600,000 a month, then maybe this becomes really valuable. Conditional embeddings, this is the prefixing that we were talking about before. So you can actually start to do things like, we talked about localizing search, but you can also influence style as well. So like a lot like you've seen these stable diffusion like prefixes of like a cyberpunk, grayscale, reality. You can start to kind of get these individual preferences baked into the query. And if you have specific user behaviors that you're trying to optimize for, like maybe you have some sort of classification of your users, you can start to encode that into your queries. I think I finished that way faster than I thought I was going to. Do I still have time left?
You have time for questions.
Okay.
This really reminds me a lot of, apologies first time. This really reminds me of the Meta Chameleon paper and their substituting models, the theoretical 34B, even though they haven't released it yet. So of course, those are research only models, but I guess the question is like, so they call it almost exactly what you said. Sorry, let me scroll to the top of the paper real quick. So they call it mixed modal autoregression, basically to do early fusion foundational models. So is it's strikingly similar. Like when you, it's very, very similar. And although you do have the, I suppose the commerce aspect more than the Chameleon paper, obviously is a Chameleon, which is an open source research thing that they pushed out. It's they show in the paper a lot of like a preference over like even GPT-4o, and like for my personal use case, when I'm doing research, the tokenizer with the created is actually quite unique, and with the basically it's all modalities, images, text, and code as discrete tokens, and uses a uniform transformer-based architecture that is trained from scratch in end-to-end fashion on 10 trillion tokens on interleaved mixed modal data. So that sounds like extremely strikingly similar. I mean, so I was wondering if you had any thoughts about that. Like it's a 34B model, so it's obviously not large. I mean, it's obviously dependent on like, who you ask, but
Yeah, I think that it's interesting and that I think you're right. You could use it in a similar sort of way. Like one thing that we are talking to people about is actually mixing the models that they're using in individual towers. So you can start to create these novel architectures. I can't speak as to what the machine learning team was thinking when they created it. Maybe there was some inspiration drawn.
Okay. Yeah, thank you. No problem.
So it seems like you need some sort of metrics for this to work. How would you recommend if someone's starting out and they want a RAG system based on embeddings, but they don't have metrics yet?
Yeah, it's a tough problem. One thing that we've been doing is this sort of vision model-based evaluation, specifically because it's multimodal. We can start to use vision models and like a mixture of vision models to assess whether results return were relevant. It comes with its own host of problems, though. I mean, you have to have some sort of eval metrics to train against, but the only way you're going to get them is launching something that has some sort of synthetic data to start with.
Sure. Thank you.
Thank you.
If you find a solution, let me know.
Hello. I know you mentioned e-commerce, but what are some other use cases you've seen with your technology?
We have there are a surprising number of use cases. We're also doing like content moderation stuff. So like people are doing NSFW detection. We have some customers doing fraud detection. We have some customers doing duplicate detection, like really large scale marketplaces, drop shipping detection. There are a lot of these like passive use cases that you can kind of just throw this model at, especially if you go into it with a result in mind and some sort of like known good metric at the end of it. So like all of those have typically some sort of human review that's gone into the output. So you have a human labeled data set already.
Yeah. So lots of classification.
And recommendation.
Any other questions?
Hi, thanks for the talk. You mentioned something around taxonomization, and I thought that was interesting. I just want to understand kind of what that looked like in practice, and kind of is there like a customer story you could talk about that?
I don't know if we have a customer story that I can talk about. I can talk through a use case where we have a lot of really early stage e-commerce companies that are playing around with how they can leverage multiple third-party sites and pull back results. But the problem is they don't have any taxonomy to start with, and they don't know they have no data around what actually works. And so the V1 problem is, how do I actually extract a consistent set of categories about the data? And typically what we see is some sort of combination of extracting data from the third parties, using their labels, some sort of language model assisted compression of that down into a smaller set of data. And then you can push that into a vector database. So instead of the items being vectorized, you have the actual categories that you want to work against. And then a real-time classification is as simple as doing a vector search and pulling back the exact nearest neighbor of one.
Got it. So it's almost like a hierarchical search and like taxonomy creation.
Yeah. And then sorry, I only talked about the first part. The second part is like iteration on that taxonomy. So like if you want to have a few different taxonomies that you're working against and you have this real stream of data, you can start to have different indices that have the new taxonomy in them and A/B test performance. So does this taxonomy perform better on my website than the initial one? And you can kind of learn from which tests work, which categories are correct, like by iterating over and over again.
Sophie behind.
Thanks. The question is that GCL, is that really in practice really applied to kind of multimodal retrieval? Or is it for any kind of generalized retrieval where ranking is important? Because those are two different,
we have a
problems.
product. We have a product that does it for multimodal out of the box today. There's no reason it doesn't work for text only as well. It's just multimodal has been our focus. And it 100%, you can encode rank into the text models as well. The use cases I've talked to people about have typically been around like enterprise knowledge retrieval.
Yeah.
So like if I know that when someone searches for something, they only click on these 3 documents, these are the relevant documents, even though they're like low down on the lexical search list.
Okay.
Does that make sense?
So the multimodal applicability is really a marketing thing. It's not technical.
Yeah, it's not, well, I think the person on the head of the team would disagree with me, but there's no inherent reason it has to be image text. And we are talking with people about things like using image bind models as well.
Thank you.
Hi, Rob. Great
Hey, Mark.
talk. 2 questions. So one, if you could talk a little bit about the cost of pre-training this model. And the other one, I'm very curious about the scores, because it seems like you are embedding the scores into the pre-trained model, whereas I feel like this is something that's kind of like fluent, and you might need to be pre-training that. It changes daily. There might be some seasonalities dependent on the vendor. And I feel like it's sort of like time series based data type. So I wonder whether it's maybe better to like join the retrieved like text and image embeddings and like join them with scores that you kind of like compute on a daily basis.
Yeah. One interesting thing that we have been doing for that problem is on the search model side. Can you keep it? Because I forgot your first question. On the search model side, one thing that we've been experimenting with is actually hot swapping the search model and keeping the actual embeddings the same. So rather than doing like a full reindexing with a new model, you can just say, hey, the Olympics have happened, and now I can't think of any Olympian's name, but now this person's name should be related to archery. And you can do that in real time by swapping out the search model. And can you repeat the first question?
What's the like more or less level of magnitude of the cost of retraining the model?
Yeah, very much depends on size. We did one a few months ago that was 500 million rows of data trained into the model. And I can't remember the exact cost, which is probably a bad thing. But we trained for a couple of days there. We could have ramped up the training, but I think it was a single instance for a couple of days, beefy instance. But I trained a model recently on a much smaller data set, about 12 million interactions, and it cost me like $20, $30, not much.
All right, thank you.
Any other questions? All right, a round of applause for our first speaker. Thank you so much.
Thank you.
All right, our next speaker is actually the CEO of Zillis, and don't worry, even though he is a CEO, he is definitely a developer. You just can't take that out of him. So Charles is, he got his master's in computer science from the University of Wisconsin. And then he decided to work at some small database company called Oracle to turn that into a cloud-based product. And what was interesting is during that time, he would go to meetups just like you folks do in his spare time. And that's when he caught the AI bug. And then a few years after that, he decided to build a project called Milvis. And because he is such a developer, he is the one that also said, hey, we're not only going to open source it, but this is getting donated to the Linux Foundation because that's how developers roll. So with that, Charles, take it away.
Thank you, Chris. Good evening, everyone. I think I can skip my self-introduction because Chris just pretty much did that. And so, yes, I'm the founder at Zillis. So Zillis is a company trying to make sense of unstructured data. And actually, we made the name ourselves. So this is Zillis means that a zillion of zillions. We use that word to representing the enormous amount of unstructured data. Yeah, so we will be able to build the world's very first vector database system since the year 2018. Yeah, so how many of you have already been using a vector database? Okay, so I saw probably like half of you already done that. So I can I'm going to be very brief on this part. So a vector database basically is a database to store embeddings, and the embeddings is very important for unstructured data because it's basically represents the semantic of the data, whether the image, whether it's a video, it's a text. The semantics is embedded in the embedding vector. And in the real world, when we want to query the data, we also want to do a semantic query. So in the past 50 years, when we are doing structured data query, the semantics and the presentation is the same. Number one means one, and you query one. But for images, for text, for videos, the embedding and the presentation is very different. That's why we need an embedding vector to represent the semantics. So yeah, so we were lucky that we started in year 2018 building the vector database system. We open sourced Milvis in early year 2019, and in the past 5 years, we will get a lot of popularities. We have more than 10,000 enterprise users. And all over the world, we have more than 70 million downloads and installations. And actually, I'm not going to talk about that. I'm going to, what I really want to share with you today is that given that large amount of installation, the enterprise user base, what do we see? What do we see in the past 5 years when it comes to building a vector database application and when it comes to build a unstructured data processing pipeline? So basically, we see that everyone wants the data infrastructure software as a database system to be very easy to use. But the company at different stages, they have a different requirement about data infra. So this is a typical stages for any startup. I think GenAI companies is not an exception. So bootstrapping, then if you really have a hit, you will have a very fast growth, and then sort of you will expansion geographically and also trying to expand your business in terms of offering more products. So for the bootstrapping stage, how many of your companies is sort of in the bootstrapping stage? I mean, like trying to build your very first GenAI application? Please raise your hand. Oh, I saw that probably like 10 of them. Yeah, so 7 years ago, when I quit from Oracle, I started Zealous, I found out that the most difficult part for bootstrapping is that you have very, very limited resources. And you want to go to the market fast because you think you have a brilliant idea and you want to seize this opportunity. And probably you just only had 1 or 2 engineers to start with. You don't want them to waste them time on building a very complex data infrastructure. Given that, you also want to prepare for the future growth. So like what if we get 1 billion users in the next 1 month and our infrastructure, we are going to have a huge burden. We want to design the structure to so can scale. So given that, so a lot of people probably, in the AI space, they want to use Python. So a vector database should be deadly easy to use. So with a pipe install, with the pip install, and you should be able to install it in 1 command line. And we have this embedded version of Mirrors called PyMirrors. You can pretty much do it with 1 single pipe install, and you just include a library, and then you can get your embed vector database up and running. And it's more than that, as I mentioned, that you want to prepare for the future. So in the future, you probably need a scalable database system. That's why we have a Mirrors Lite. So as I mentioned, PyMirrors, but we also have a dedicated server version of Mirrors, which is a distributed version. You can easily scale to 100 nodes, even 1,000 nodes. But across the board, between Mirrors Lite, and this cloud, we offer the same API, we offer the same SDK, which means you only need to write your code once. And you don't have to rewrite the code every time you hit the next milestone, you get a next 1 million users, you don't have to do it. And so we were lucky. So we were lucky that suppose we were lucky, everything goes fine. We get a 10 million users, and it keep growing. Then at this growing stage, we may probably think about cost optimization. Probably like this cloud cost and infrastructure cost going to be cost you billions or 10 billions. So in the meanwhile, that as the user base grows, you probably want to start to think about scalability. So the status quo about vector database, unfortunately, is that it's very expensive. When you hit into a point, like if you get 100 million, 1 billion vectors, it's going to be very expensive. And it's, so it is because that most of these vector database solutions that are, they are pure in-memory solution. You have to put all the embedding data in memory. We know that memory is not only very limited, but also very expensive. So for example, HNSW is a very popular vector embedding algorithm, and it's pure in memory. So, and also if you put all the data in the memory, it's not going to scale. So, so at Zedis that we offer a disk solution. So with the disk that you probably not only have like 10 times lower the cost, but you can put 10 times more data in your database system. And also more than that, on the we also can use object store and even S3 S3 kind of storage on public cloud to help you to put the data on public object store, can further lower down the cost and also give you more capacity. You can store more data. So how can we do that? So first of all, what we did is storage and the computation separation. So so if you put all the data in the memory, it's pretty much like you put the storage and the computation in a single instance. And this approach is not going to scale because if you want to scale, you have to scale the storage layer and the computation layer simultaneously, and it's going to be very costly. So it's impractical. And also, and the other end is that if you put if you don't have a storage computation separation, the data, you can only process the data that are attached to this instance, which means that you can only access and process local data, and it's not going to scale. So that's why 5 years ago, when we started the Meerverse, we have make our mind that we should have this we should decouple storage from computation. So if you look at our architecture here, so on the right side we have the worker nodes. So the worker nodes basically they are doing computation, they are doing queries, they are doing indexing building. And also we have a data nodes. So data nodes is what we put the data, and the data nodes and can use your local storage, can use S3, can use object store as a storage. So so as we can see that with the computation and the storage separation, we can do this hierarchical data storage and the caching. So, so as I mentioned, that most of the status quo solution, they are working on the first tier. So they put all the data in the memory, basically HDRAM, and this. So this is very expensive, but this solution can offer you very high performance. So in terms of latency, but you cannot put much data in an instance. So probably it's bounded by around 100 gigabytes of memory. Depends on how big instance you are running. But on the tier 2, so in our architecture, we are using SSD, we are using local storage, high performance local storage as second tier. So as we can see that on the second tier, you can probably put like more than 50 times more data. But the challenge is that you will sacrifice the latency because disk access is going to be slower than memory access. So here we did a tons of optimization, and I'm going to talk about one optimization in a second. That so our solution can let you to put your data in a high performance local disk without sacrificing the performance. So if you look at the performance, it's about the same as a memory solution. And then the third tier that we can use distributed local storage. So to put the data to can get more capacity, but since we are introducing distributed storage, the performance will be lower down a little bit. but still in the range of milliseconds. So a lot of a lot of solution is okay with that. And then on the last tiers, we have object storage. And so the object storage itself will introduce more than 10 milliseconds in terms of latency. And so that's why we also did a lot of integration. We are not just put the data on S3, for example. We are building this hierarchical caching layer. So what we did here is that it's very simple. It's just it's just a data caching. It's a 4-layer data caching. So on every single layer, we are going to find out what is hot data, what is sort of cold data. So we put a cold data in a low speed storage, and not only to achieve the scalability, but also hugely reduce the cost. So so given that, so we have a data storage and computation decoupling, and we can definitely achieve higher scalability. So nowadays that we on a single instance, so we can support up to 10 billion vectors. So 10 billion vector basically so if you are running like a popular application like a Canvas, like a Lotion AI, you're probably hitting like 10 billion vectors. So I mean that you need more than 100 million active users, and you will get more than 10 billion vectors. So 10 billion is sufficient for most application developers. And more than that is that so we can also scale out. We can scale out, so we can have multiple instances. So one of the largest deployment of Aamir, we can support up to 100 billion vectors. So 100 billion vector is something that we are considering like a web scale. So for example, if you are going to index every single web pages on the internet, it's probably around like 600 billion vectors, and at that scale. So we can scale out to support web scale applications. So how we can achieve that kind of high scalability? So this is overall architecture of Aamir. So first of all, you can see that we decoupled the single system into a lot of microservices. So we see that we have coordinators, we have a workload, and in terms of workload, we also have a different load, query load, so which is in charge of data queries, and we get a data node was in charge of data synchronization, data consistency, and also we have an indexing node. So basically, it's a powerhouse to build the index, the high dimensional index behind the scene. And we support we separate our computation from storage, and also we have a distributed messaging queue for data consistency. So it's sort of like distributed way write-ahead log. So we can we can ensure data consistency without sacrificing real-time data accessibility. And so and what we found out that for a lot of these well-established companies that when they hit to the expansion stage, they will have some further requirement in terms of performance, for example, and also they are kind of worried about I cannot build my my application, my business on a closed source solution because this means vendor lock-in. They don't want that, and also they probably running on several cloud vendors. So they need a multi-cloud solution, and they want a global availability. So given that, so for this large enterprise, since performance is very, very critical, so we build an open source a benchmarking system for vector database systems, and it's open source on GitHub. And so here are some preliminary results. So ZDs versus Mirrorverse versus Pinecone, but on this website you can see there are far more comparison results. So basically, in the past 1 year, after we released this benchmarking, we received a lot of requests from vector database vendors, from MongoDB, Redis, Elasticsearch. They are all participating in this benchmarking. And yeah, so if you want to find out what vector database performs the most for your application, you definitely want to check it out. And yeah, so multi-cloud. So this is running on top of open source, so you don't have this worry about vendor locking, but also it supports multiple clouds. So at this moment, we are running on AWS, Azure, and Google Cloud. And also globally, we are supporting more than 20 availability zones geographically. So from North America to Europe to Asia Pacific. And yeah, so I just shared that like for company at the different stages, you may have a different requirement for vector database. And and lastly, I want to share a little bit about what we see as vector database applications. So first of all, RAG is a very important application of a vector database. I would say that's the first killer application. So I think probably a lot of, I suppose most of you already understand what's a RAG system. And what I found out that in the past few months, there's a debate about a RAG or not a RAG, and yeah. So, but in my opinion, that a RAG is not about technology, because a lot of people are arguing about that there are some other technology alternatives. Maybe RAG is going to be an obsolete technology, but in my opinion, I think RAG is more than a technology. It's a business model. So basically, it's a business model that fill the gap between public domain data and the private domain data. So as an application builder, you want to keep your private data, because that's the data. So that's your asset. You don't want to give the data away to large language model companies, for example. So you want to have this data sovereignty, and also you just cannot share the data with all these large language model providers. So that's why you need a RAG system. So you want to keep your data, but you still want to take advantage of large language models. So in the past 1 year, we definitely saw the evolution of our RAG system. So last year, we saw a lot of application about a text, about documents, and they are using like GPT 3.5, GPT 4 to build the applications. And early this year, with the release of a GPT-4 Omni, we saw a lot of applications for multimodality. And so it's not so with the multimodality, you can also you can start using your private data, such as images and videos. You can feed those data into a large language model to enhance its knowledge. And it was last month at this meetup that Frank Liu, our machine learning architect, gave a wonderful presentation about how you can build a multimodality AI applications. If you guys are interested, check it out. I think it's on the YouTube channel already. And I'm going to make a prediction of next year. So in the previous presentation that we talked a lot about recommendation systems, and talking about so basically recommendation system is trying to make sense of another type of unstructured data, which is user behavior. And in the past 1 year, we saw there are more and more recommendation systems that are powered by larger foundation models. And also we are working with NVIDIA on this open source project called Money. So Money is an open source framework for you to build a very efficient recommendation system on top of a vector database and also user profile informations. And so what I see is that in the next year, there could be another foundation model. And so you can, so actually this is this is very, very beneficial to a lot of online business because recommendation system is so important. But for a lot of startups that they don't have enough data, they don't have enough user data to build their very first recommendation system. So for example, you have an application, you only get like 500,000 users. Probably it's not a good idea for you to build your own customized recommendation system because like 500,000 users is not a lot to build to build a solid recommendation system. But what about a company like a Meta, company like Walmart, or could it be TikTok? They can sort of build an open source foundation model for recommendation systems, and they share or provide a service to other companies. And so at least you still need to do some fine tuning. You wanted to do some data enhancement with a RAG-like solution, but at least you have something to begin with. Even you get only like 10K users, 100K users, you get something to start with. So that's what I see in the future for recommendation system. And so vector database has a lot of application areas, not only to RAG and recommendation, but also for real-time ads, for autonomous driving, and for fraud detection, data security, and also drug discovery. And there are a lot of pharmaceutical companies that are trying to use vector analysis to analyze the 3D structure for molecules, 3D structure for proteins to do virtual drug discovery. And so that's pretty much my sharing today. And I'm ready to take questions.
All right.
Thank you.
Hello. Do you ever think that fine-tuned models like local, cheap, fast, fine-tuned models could ever replace or compete with vector databases or RAG systems?
I would say that they are going to be coexist for quite a long time. And so for the problem with the fine-tuning is that first, you probably need a few PhDs in your team to do fine-tuning. It's not easy at all. And also the other thing is that fine-tuning, you may get a very good result, or you may get nothing in the next 3 months. And there are a lot of issues that if your data are polluted, and the whole model will collapse, and you get nothing. So fine-tuning is not predictable. So on the other end, vector database can pretty much, in terms of accuracy, I would say that it's not as accurate. It's not as accurate as a fine-tuned model, but it can still achieve the probably like around 19%, 95% of the accuracy of a well-tuned model. But it will give you much more certainty. So with the RAG system, you know that you are going to build your RAG system in the next 1 week, and you can get it up and running. And you probably only need one or two developers to do that. You don't need a number of PhD to do that. So I would say that the cost of fine tune is much higher, and also the uncertainty to fine tune a model is also much higher.
Thank you.
I like the graph you had about the tier 1 and tier 2 storage, and then you had the RAM and then the NVMe. Are you re-implementing algorithms for NVMe because there's a you can call mmap, and then you can map the NVMe derived directly, and then it can appear as both RAM or disk?
Yes. So we already support that. So if you look at our open source code base, you will see we already supporting map 2 years ago. So basically, you can map some part of your local disk, and to have the mirrors to use it as a virtual storage, and we will take care of data swapping for you automatically.
Cool, thank you.
Hi, I have a question over here.
Mm-hmm.
And I just need to know that Milvus and Celis is just for scalability, or you also work with startups. But if you do scalability, do you also benchmark against like non-cloud ones, like for example, like any scale with CPU, GPU kind of solution? Yeah, that's my question.
Yeah. So here that for early stage startups that as I mentioned, that we do have a Mirror Lite, so you can pretty much do install it with just a pip install, and also I'm here so to get the best performance. We it's not in this presentation, but also we embrace hierarchical computation. So our Mirrors project can support a wide a great variety of processors, from GPU, from ARM processor, from definitely like support of the processor from AMD and Intel. And for example, it was early this year we announced the world's very first vector GPU accelerated vector database within NVIDIA. So we have been working with NVIDIA for the past 2 years, and so with the GPU acceleration, you can think of that it is that so on top of a tier 1, we have another tier, probably called tier 0. So it's a memory, it's on-chip memory of a GPU processor. You can put a part of the data in the GPU memory, and to use the GPU, the parallel computation of a GPU to further accelerate the vector database processing. Thank you.
Hi, Charles. Thanks and appreciate your structured talk. I'm very curious whether you have use cases of sort of building hybrid vector storages, having embedded systems, embedded vector database, Milvus specifically, and blending it with the cloud version due to some constraints of the devices.
Can you repeat the question again?
Sure, of course. So I work with clients who have certain limitations on devices or like data privacy, so they don't want or can't go to cloud, so they use sometimes open source projects, and they sort of use embedded vector databases on kind of like resource poor devices. And I'm wondering, like, what are potential use cases that you already have, or maybe we're in talks with some enterprise clients where you'd have to use embedded vector databases sort of built in a hybrid system with the cloud version.
Yeah, great. So, so actually, so this is a great question, and actually, even it's not mentioned in this presentation. Actually, we're already doing that. So what we see here is that the future of AI is going to be we're going to have a bunch of centralized models which are running on cloud and probably owned by OpenAI and Anthropic. And those models offer you the highest performance, but you need a lot of computation. And but also we're going to see a lot of these lightweighted models deployed on edge devices, from a cell phone, from a tablet. It could be from even a light walking device like a router. And so deployed on the edge. So so the way we make Mirror's Lite, actually Mirror's is embedded. And so in the past 1 year, we were seeing more and more demands from smartphone manufacturers. So for example, I just cannot mention their name. And but we are working with some of the largest cell phone vendors to help them to get an embedded vector database to running on every single cell phone and the tablet. Yeah, and also it's more than that. And there's another way of edge computing that we have this autonomous driving vehicles. And this vehicle has all this sensor data, camera data, and they also need an embedded vector database on each vehicle, every single vehicle. So with a vector database on a cell phone, on a tablet, on autonomous driving vehicles, that you can pretty much like process pre-process a lot of data on the edge devices, and you only send a very small percentage of the data to the cloud for some heavy lifting computation. And this is good for latency and also for cost reduction. What? Yeah, so actually we didn't decide that, and so basically the application builders, they decide that. So in terms of smartphone builders, they are so. But what we see is that it's sort of that so in terms of GenAI embedded a cell phone, and so if this data or this data can be processed by a lightweighted small model, and they just do it on the cell phone. They don't want to send data over because for not only for better user experience, but also they want to cut the cost. And so basically, if you can do an inference on the cell phone, theoretically you don't have to pay for it. So because so it's but if you send it to the cloud, you have to pay for the computation. And also what we found out that for a lot of autonomous driving applications, that they will decided whether the data needs to be persistent in the cloud. If the data, they want to keep the data, they send the data over. Otherwise, they process the data and they just discard the data. Yeah.
I have a question.
Well,
here.
Go ahead.
Thank you. You mentioned hot data and cold data. How do you define the hot data?
Yeah.
And is that hot data static, or at what point do you change it? And
yeah, so actually this is a very good question. I probably can spend another 1 or 2 hours to explain this in detail to you, but to be brief is that actually inside of Meerverse database, we are using a lot of this AI algorithm and machine algorithm to power our execution engine. So Meerverse is not just a database built for AI, but it's an AI database, which means that so for example, to find out which data is hot data, which data is hard data, or the cold data, we don't have a schema. We don't have a predefined schema to define. But if you get more and more data running our platform, we can sort of we have a auto tuning algorithm that can find out your data access pattern. So we decided to do that because we found out that every application pretty much have their own data access pattern. So hot data for one application doesn't mean it's a hot data for the other one. So we have this machine learning algorithm to learn the pattern, and then we can put the data, we can put the hot data in a faster storage, and also we can predict which data we have a highly the chance we are going to access in the next 10 minutes or 5 minutes, and we are going to do data proficient, but it's all based on machine learning.
Okay, one last question.
So I'd like to thank you guys for open sourcing a lot of Milvis and also sponsoring some of the hackathons I've actually participated in and done pretty well. And sadly, have not been able to use Milvis Lite that often, but very much so. I've been interested in I'm in the bootstrap phase of my startup. So I've been looking into Optane storage, and I don't know if Milvis has any kind of known compatibility with it, because it's very cheap and it's very much similar to RAM, and it's like I guess in theory it would be between the lines of a RAM and NVMe, and because it goes into the RDIMM slots and whatnot. So I don't know if anybody's ever attempted a I just literally. In fact, it's so easy to launch Milvis Lite. I didn't even realize, I was going through my laptop and I just pip installed Milvis Lite, and it just launched a client, and I connected. I was like, okay, I probably should have used it. So instead we tuned a model, but that's a different story. But I was wondering if you have any information on if for somebody who's very scrappy, very much needs to cut costs, if you're running on something local, if any Optane based basically deployments of Milvis, especially Milvis Lite, or maybe just Milvis full fat.
Yeah. So actually, you know what? That we are working with some vendors with that for so for this particular case that we will be working with the Intel. So we're trying to find how we can get a Milvis up and running. And this is still not released yet, but it's an ongoing so ongoing project, and but we think this is pretty much doable. We didn't see any technology blockers that we cannot do it. But also, Milvis is an open source project. If you want to participate, you want to contribute your code, and you're welcome to do that.
That'd be great.
Thank you.
Cool. All right. Thank you so much. Let's give Charles another round of applause. And then let's switch gears back to training. Come here, Aamir. So our next speaker is the co-founder of Mixed Bread AI. And if you look him up on LinkedIn, you'll be happy to know that his title is Baker, which I thought was really cool. I guess this is something that they do at the company. I mean, when you have a company named Mixed Bread, you can have a lot of fun with that. So let's go and get started.
Hey, so once it's up there, so shortly about me, I'm Aamir. I'm the co-founder of Mixed Bread. Been doing representation learning for the past 6 years. So before it got hot, and now we are on it, and it's not loading.
just plug it
Yes,
in
I
and
think
again.
just do it there. Okay, I'm seeing it there. Okay, cool. Yeah, the title of the speech is today, Baking the Future of Neural Search, How to Train a State-of-the-Art Embedding Model. So before I jump in, you can find the slides here and then you don't need to make pictures all the during the presentation and you can listen. So shortly about Mixspread, we've been around for 8 months. So we are building embedding models, re-ranking model, are specialized on search. And so far we have over 7 million downloads. We also help reducing costs for embeddings, so storing them. So up to 64 times, people are using us in production and state-of-the-art power. So cool. Before we jump into, I just want to quickly outline why embeddings matter, especially for unstructured data, especially if massive amount of unstructured data. Think of logs or internal documentation and so on and so forth. Embeddings gives us a possibility to encode information into a mathematical representation and operate on top of them, which helps you to cluster information to gain quick insights into large amounts of data, find outliers in massive data sets, and also do search over it. And the cool thing is it's a mathematical representation. So the input data almost doesn't matter. It can be video, audio, text, and so on and so forth. And all languages as well. So I want to use our embedding model as a case study to showcase how you train those models and how you turn them into production and can turn them pretty efficiently into production. So our model was released 4 months ago, I think, is state of the art. So it's super small, it's 300 parameters only, outperforms the models from OpenAI and Cohere on public and private benchmarks. And it's freely available on Hugging Face. And it's trained with compression methods, which were already mentioned in the first talk, like Matroshka and binary embeddings, which helps you to store up to 64 times the storage cost. And after this talk, I will show you a demo how you can search whole Wikipedia with semantic search on a toaster. So stay tuned. So if we do semantics, if we do search, let's think about it, like, right? So back then, if you're searching in Windows for PDF documents, a class, or my brother, for example, is selling trains and he's searching for trains and he wants to also find relevant information around trains, for example, train station, railway stations, or subways, and so on and so forth. He couldn't do that with traditional search because traditional search would just go through every document and see if the word train occurs or not. So those searches are just based on text. So for example, if you also want to find images of trains, you couldn't do that with that. And also you have ambiguous words. So for example, if I search for apples, do I mean the fruit apple or do I mean the brand? And also the word order is not preserved. So meaning if you think about it, if you do keyword search, you have no real connection for nouns and the verbs before it. For example, also if I search not apple, I couldn't really represent that with traditional search. And there's also lexical gaps which are normally solved through query rewriting. For example, if I search for rag, it would never match retrieval augmented generation. And you have way more shortcomings of that. And here dense representation or embeddings come as a rescue. So we actually just mathematically have a text or whatever input, give it to in a function, and then retrieve a vector which represents this information semantic meaningfully. So n is here the dimension of embeddings. And those embeddings models are normally transformer models like our Mixspread embedding models. So as an example, we put in bread is amazing and get out a 1024 sized vector. So on top of those embeddings, as I mentioned, we can do cool stuff. We can do clustering, bitext mining, meaning if you want to train a translation model for your LLM, you could have a multimodal model where you put in English text and get out, for example, German text. You can do semantic search, multimodal search, and also search through all modalities. So I don't know why it's here, but so one issue, so before I jump into all this stuff, just as a warning, and I think this will help to understand why RAG fails mostly and what you can do better, is that if the model's never seen the data about your domain, they don't know what's going on, and they will likely perform really, really bad. And also, like everyone hates chunking, right? So if you ever build RAG apps, you need to chunk, and it sucks. But the issue why we need, or the reason why we need chunking is, if you think about, if you have a sentence, Like first sentence is about this meetup, second sentence is about the elections, and the third sentence is about Dogecoins. How do we want to really represent it meaningful in one vector? So when we search for it, that we can really get all details of this whole sentence. So embeddings really work if the topic you are talking about is, or the text you're talking about, or the information you have is about one topic. So that's why long context normally doesn't work. And also, if you train a model once, you can do some tricks as showed in the first talk, but they still need fine-tuning to inject new knowledge. So this means before using any model or trying out anything, build an eval set and have a data set and try the model on your own set. So about our model, so how it was trained. It was initialized from a BERT large uncased and was pre-trained on over 700 million pairs using constructive learning. So the contractive learning I will explain in a bit, and was fine-tuned with over 30 million high-quality negative triplets. Sorry, I just need to figure out where my slide is gone. One slide is gone. Okay, my most important slide is gone, so I will just improvise now and open up an old one. Super. From an old meetup with Haystack, and explain it through that. Okay, cool. How is this model trained? So we have this BERT model, right, which is just saw a lot of bunch of text, and so it produces some vector in the end. So we have now this data set where we go through the whole web and try to find stuff like news article, websites, where we have the heading and the content or description and so on and so forth. Or if you think about Anki cards, like flashcards, I don't know if you've ever used Anki, there you have a question and an answer. So you have a query and a positive pair. So what happens now? So you put in an anchor, so this is a query, and you normally have a positive for every query in your data set. So this you put in as well. And then you use the positive data from the other samples and treat them as negative. And what constructive learning wants to achieve is that the anchor and the positive pair are pretty close, and that the negatives are pretty further away. So what the model actually does and why it fails is it tries to guess a point in the space where it thinks semantically this data is relied, for example, I love bread. And then we try to model it that it makes sense by injecting this constructive learning. So meaning putting it away from negatives and putting it closer, putting the positives closer to the anchors. So, and those negatives, as you can think about, matters a lot. So the higher quality the negatives, the better the model understands how the world around him works, and the better your embeddings are in the end, and the better they will perform on your benchmarks. And that's why I also was talking about why it matters that it has to be trained on your data. Now think about, the model is just guessing this point in this room, right? And if we, for example, we're training it on biochemistry, and now we want to use it for finance, but it never saw data about finance. How can it know where to guess, for example, the yen or euro and so on and so forth? So it becomes super hard for the model to really guess and understand where to modulate those data points. So that's actually why normally those model fails if they haven't seen your data and they really generalize badly. So talking about high quality negatives. So, all right, we have this anchor, we have this positive. And think about the following. Imagine you're positive and your query is about, hey, what is COVID? And your anchor, that's a query, and your positive is about a description of COVID. And your negatives now about talking Coke. So you understand? So if you have, for example, COVID could be also a nice beer, right? So it becomes super relevant how the negative is really structured to give the model a good understanding of the world. So the better your negatives are, the better the model understands the real world and also the fine-grainer it gets. So that's why you should spend most of your time doing mining hard negatives. And we came up with novel algorithms, which I can't present unfortunately here, but maybe once we're big enough, we can just open source them to mine those negatives and build such a good model for its size. So if you think about, our models has 300 million parameters, and our competitors have models with 7 billion plus parameters. Ours is optimized to run inference even on CPU. So yeah, that's what I was talking about. So this pairs in the beginning, like question answer pairs, having also document titles and document description, news titles and news description. We crawled over 700 million pairs, and most of our compute was used to actually crawling instead of training this model. And for the high quality triplets, we have over 30 million pairs. And here we scrolled a lot of social media to actually get user signals to train the model and figure out negatives and also tune models to create those negatives. And who does know the MTAP here, the massive text embeddings benchmark? So that's a quasi standard benchmark in industry. And most people are right now overfitting to those benchmarks. And as I explained to you, if you don't train on the data you are interested in, they don't generalize well. But MTAFs gives us a good way to understand how well models generalize. That's why we train with absolutely no overlap on this test benchmarks, because also constructing those test benchmarks sucks, and we can use our time for better things. So now we have those embedding models, they're amazing. And our first customer comes to us and say, hey guys, I have 30 billion embeddings I want to store. Yeah. Want to store. So if you would just naively store, like think about, you have 1024 embeddings, dimensions, and for every dimension you're storing 32 bits. And for this 32 bits, if you would store 100 million embeddings, it would cost you $1,500. And if you would store 250 million embeddings, it would cost you $3,600. And if you would store like 1 billion embeddings, it would cost you around $15,000. And it's extremely expensive because this guy had like, those guys had over 20 billion embeddings to store. So we need a better way against like next to putting them on memory storage to reduce the memory footprint. And here compression comes in. Different types of compression exist. And the idea of compression is just one thing. Hey guys, reduce memory and have as much performance as possible. So one type of it is binary quantization. And here it means instead of storing one float per dimension, we just store 1 bit. So meaning we just cut down the cost by factor of 32. Another thing is open source by done by OpenAI's Matroska representation learning. And here the idea is instead of having one big vector, for example, 1024 dimensions, we have also subvectors in there, which are optimized to be used also for semantic search. So instead of, for example, taking the full 1024 vectors, we take the first 512 vectors or the first 128 vectors and so on and so forth. And the model is optimized that most information is also saved in the first embedding vectors. Or you are super fancy like us and you combine both of them. You just don't offer binary quantization, but you also offer Matroska representation learning on top of those binary embeddings. Meaning if you just store instead of 1024 512 dimensions, you get a 2 times cost saving, and you do on top of that binary embeddings, and you get 64 times cost savings while maintaining still over 92% of the performance, which is really, really good enough for most RAG use cases, but I wouldn't use it, for example, for e-commerce. So let's just look into a bit of the results I was mentioning. So as I mentioned, like binary quantization is just instead of storing 32 bits, I store 1 bit per dimension. So we have 30 times less memory, so which translates directly into 30 times cost savings. And the cool thing is, if you think about how vector search works, right? It's cosine similarity. It's a lot of vector multiplications, dot product. And what binary embeddings allows you to do is doing Hamming distance, meaning you just have 2 CPU cycles, pop count and XOR, which is blazingly fast on all modern CPUs. And that's how you can get even 40 times faster retrieval by using that. And how can you convert a float embedding into a binary embedding? You just do simple thresholding. So if the value is larger than 0 per dimension, you give it a 1, else you just put in a 0. And then you do tag bits in Python, for example, and you're more or less done. And we are obviously, or we are not the only ones doing that at the moment. Korea also published a model for that. And if you look at the MTAP retrieval, which is a really large scale benchmark, you see that our performance drop is just 96.45, like only 3.55%. And for Korea, it's a bit more. And if a model is not optimized for that, for example, the E5 base V2, you get a severe performance hit. So you specifically need a model which is trained for that to be used in production. So I was talking also a bit about binary MRL. So on the dimension side, we have the dimensions we store. So the origin dimension is 1024, and we go down to 8 and almost no information. And on the y-axis, we see the NDCG at 10. So, and the yellow ones are the binary embeddings, and the orange one are the floats embeddings. And as you can see, actually for 512 and 256, we're pretty close to origin performance, and same for binary, and they move together. So, and what we see in production is this works really, really well for large-scale use cases. So just again, like a more direct comparison. Sorry for my Denglish. So I'm normally a German natural speaker and it moves around. So if we would store 1 billion embeddings with float 32, we would pay around 14.5K per month on AWS. And if we go down to binary Matroshka, it's going to be $226 only. So as you can see, it's a huge cost saver for really using semantic search and also vectors or embeddings in real life production use cases. And we also believe that this type of technology enables new use cases, which were not possible before because of cost, basically. So I will move back to the old slides because I had one thing there. I wanted to show the demo. Okay, I promised I will show you how to search Wikipedia on a toaster, right? At the beginning of search. And toaster means, I don't know how much a toaster costs in the US, but this server is hosted on a $20 Hetzner machine in Germany. And it's the whole English-speaking Wikipedia, which is around 42 million embeddings, which you can search actually in sub 200 milliseconds. And for example, we have this cool query. Who are the founders of GitHub? It needs a bit, then you can see like, nice Tom, Fritz, and Werner. I Googled it, makes sense, it's right. So you can also double check. As you can see, it's like 150 milliseconds roundabout real search time you're getting, plus re-ranking. And that's just hosted on a $20 machine in Germany. So yeah, nice. Before I stop, any questions? You can follow us on LinkedIn and Twitter. And guys, we just raised our seat. We are hiring, so please apply.
So I vividly remember the launch of your model because it was extremely exceptional with the chart that you had when you were launching it. I just noticed though that the burning question I've had for I suppose you or anybody on your team is I see you guys have the max positional embeddings at 512 on your, and thank you for the Apache 2.0. Always prefer that, you know, a great, thank you for the model. And but it's just is there any, I saw also today 1024, right? So is there another model that we don't know about, or is that just, am I looking at the wrong model here?
So you mean regarding the dimensions, right?
Yeah, so I'm looking at Mbaxi embed large v1, and I know that so within the config.json, the specifically the max positional embeddings 512, the context.
Yes, they refer to the context exactly. So it's 512's context window.
Okay, but I swear I saw 20. No?
This was the dimension of the vectors.
Oh, okay.
Out, yeah.
Sorry, apologies.
Yeah.
So that was, but is there any advantage? I mean, 512 obviously is very small, although, you know, obviously you've gotten it very efficient. Is there any advantage to creating a larger context window model?
Yeah, I was referring to that during the talk, right? So larger context doesn't work for a lot of real life use cases because think about it. You have one single vector, right? Where you want to compress all information you're getting out of the context. And now let's say your context or your text you're giving it as input. The first sentence is about the US election. The second talk is about this meetup. And your third sentence or paragraph is about Coca-Cola, whatever, right? It's insanely hard to map all this information into one single vector. And that's the false promise long context retrieval is giving you. So where embedding models work exceptionally well is if you have just one topic, clearly talking about one thing, not going back and forth negotiating, they're extremely well on that. If you move further away, it gets harder and harder for those models to compress all those information into one vector. So that's why we are, for example, really skeptical about long context retrieval with one vector, but we are researching actively into making long context possible with larger, with more or multi-vector representation.
Thank you so much.
Hello. So I had a question kind of about chunking. Sort of your approach relies on splitting text into smaller chunks that you can then generate a vector for them. And that vector kind of has a single meaning, the issue we were talking about, where if you have a long context, then there's kind of multiple possible things that could be in your, multiple meanings in that piece of text. So you really want to chunk things up into pretty small chunks. Have you found a good solution to chunking data?
I think there was this amazing blog post from ChromaDB where they researched different chunking strategies. So what we see in production, just doing sentence splittings works exceptionally well and just do it by token. And Chroma introduced a new chunking method, which they call semantic chunking, where they starting clustering stuff around and see, hey, how similar are things? I can really recommend just reading the blog post, and they have also a really good code base where you can just scroll through.
Awesome.
Hello. Do we have to speak German to apply?
No.
Danke.
Cool. So I was quick, so we have more time for networking, guys.
All right. Thank you so much. Another round of applause.